So hello everyone, this time we will be talking about the molecular nature of lipids in foods and living systems. So this PowerPoint is from Dr. from Gloria Jesus Baltazar. We just used it because we lack already time to prepare. So these are the summary of our biochemical substances. We have two major categories, which are bioinorganic substances and bioorganic substances. And under our bioorganic substances, we can have our lipids, which is about 8% of that biochemical substances found in living systems. So we will be talking in this presentation about lipids. So you can see here a picture who is Michael Cooper that has cut his calorie intake to nearly half of the daily requirement. So as you can see, he does not have any fat storage, thus he faces the following problem. He looks sick because he has a bad complexion or look, and also he feels terribly cold even at 20 degrees Celsius because he has no insulation. And another thing, he cannot afford to starve even for a few days because he has no fat stored to sustain survival. So if you can see people who has a chubby body or who has a lot of fats, well, those fats doesn't only contribute to bad things in the body, but essentially those are macromolecules in the body that we need to have in order to maintain proper homeostasis and balance. So in this presentation, we will be talking about lipids and its importance in living systems. So when we say lipids, these are considered as heterogeneous class of naturally occurring organic compound classified together on the basis of their common solubility properties. You have to take note that when you can read lipids, they are already insoluble or immiscible in water, meaning they are hydrophobic in nature or non-polar. So they can only be soluble in non-polar solvents because in chemistry, like dissolves like. Polar substances dissolves in polar substances, while non-polar substances also dissolves in non-polar substances. So these lipids can only be soluble in organic solvents that are nonpolar, like diethyl ether, chloroform, and acetone. Okay, so you have to take that in mind that lipid is an organic compound found in living organisms that are insoluble or sparingly soluble in water, but soluble in non-polar organic solvents. So if you can picture out a water with an oil, so you consider your lipid as an oil. It doesn't go well together with water. So that is the characteristic of our lipids. So examples of lipids include fat with a structure, a biological wax, a steroid, a glycerophospholipid, a sphingolipid, and a sphingoglycolipid. So we can classify lipids based on their biochemical function. So our lipids has 5 biochemical function. We can use them for energy storage. Those are the triacylglycerols group of lipids. For membrane lipids, we can find in our cell membrane of phospholipids, sphingoglycolipids, cholesterol, and emulsification lipids, which are found in our bile acids. We also have messenger lipids, which are the steroid hormones and eicosanoids. And we can also have protective coating lipids, which are considered as the biological waxes. Another criteria to classify lipids is based on whether or not saponification occurs when a lipid is placed in basic aqueous solution. So we have lipids that are saponifiable and we have lipids that are non-saponifiable. So these saponifiable lipids are converted into smaller molecules when hydrolysis occurs. So these are triacylglycerols, phospholipids, sphingolipids, and biological waxes. While these non-saponifiable saponifiable lipids cannot be broken up into smaller units since they do not react with water. So this includes cholesterol, steroid hormones, bile acids, and eicosanoids. So based on this schematic diagram, we can simplify the categorization of lipids into simple lipids, compound lipids, and derived lipids. Under simple lipids, we have esters of fatty acids. When we say esters, we can have this functional group, which is R, C, I'm sorry, C double bond O. I cannot have this good writing. You can have this, I'm sorry, wait lang. When we have esters, you have to take note that the functional group of esters is R, C double bond O, OR. So these R here are the hydrocarbon chains. So we can have these esters of fatty acids. So this could be a long hydrocarbon chain due to our fatty acid um, in that ester functional group. So under the simple lipids, we can have these fats, which are the esters of fatty acids and glycerols. And we can also have waxes, which are esters of long-chain fatty acids and long-chain alcohols. So we also have compound lipids, which are esters of fatty acids, and alcohol contain other groups also. So they have esters of fatty acids connected to that functional group. So they have fatty acids right here, and also in the chain, they can have other functional groups or other groups connected to it. So we term that as compound lipids. And we also have derived lipids, which are composed of a hydrocarbon ring and a long hydrocarbon side chain. So those can be classifications of lipids based on their complexity. So the main groups under the simple lipids, we can have the tags or triglycerols or triacylglycerols, fats and oils. And we can also have the waxes here under the simple lipids. Under the complex lipids, remember that they are still esters of fatty acids, but they already contain other groups. So in this case, we can have the phospholipids. So from the word phospho, meaning there is a phosphate in this structure. So under these phospholipids, we can have these glycerophospholipids and sphingophospholipids. And under the glycolipids, remember glyco, we already talked about carbohydrates when we have the term glyco or glycans, meaning there are sugars attached. So under here, there are sugars attached on these lipids. So under glycolipids, we can have the cerebrosides, globosides, gangliosides, and sulfatides. So those are main classifications of lipids according to their structure. So let's talk about simple lipids, and let's start it off with fatty acids. So this is a familiar word to you, fatty acids. And this is most frequently encountered lipid building block or structural unit. And this fatty acid is a naturally occurring monocarboxylic acid, meaning it only have one carboxylic acid in its structure, and also it has its long hydrocarbon chain. So that's why this is called as an organic acid, because it has a carboxylic acid connecting to that long hydrocarbon chain. If we are going to deduce the structure of this fatty acid, we can have or we can see an acid end due to that carboxylic acid, and we can see this metal end due to this end from the long hydrocarbon chain. And these fatty acids are actually made up of long hydrophobic hydrocarbon chain that can range from 4 to 36 carbons. So these lipids, especially these simple lipids na fatty acids, are considered to be non-polar because of this long hydrocarbon chain. So it has a great surface area when in contact with those polar solvents of this long hydrocarbon chain, and it can only have London dispersion forces of intermolecular attraction to other solvents, so it cannot have a great electrostatic attraction or extent of hydrogen bonding when in contact to other solution. So it is really considered that these fatty acids are insoluble or sparingly soluble in water because of this hydrocarbon chain. So in fatty acids, remember, we have this carboxyl group and we have this hydrocarbon chain. This carboxyl group has oxygen in the structure. They still have the ability to do hydrogen bonding. So this is what we call the polar group in this fatty acid. While this hydrocarbon chain is what we call the non-polar group in these fatty acids. So both polar and non-polar properties are still present in our fatty acid, but these non-polar groups are very dominant in the structure. However, we can consider these fatty acids as amphipathic. So when we say amphipathic, it can have this polar and non-polar properties. But generally, since the hydrocarbon chain has the greater surface area when in contact with other solvents, and it can only have London dispersion forces or van der Waals na interaction with other solvents, they are generally considered as hydrophobic or non-polar. So these are additional characteristics of fatty acids. Again, they have long straight chain and they doesn't have branching. So they only have one carboxylic acid in the structure. And it can also have even number of carbon atoms, usually from 12 to 24. So our fatty acids can be classified either into saturated fatty acids or unsaturated fatty acids. You have to remember when we talk about saturated fatty acids, meaning they do not have double bonds in the structure. But when we talk about unsaturated fatty acids, meaning they contain one or more carbon-to-carbon double bonds. And usually the first double bond is located at the 9th carbon. And when it has a double bond in the structure, especially for unsaturated fatty acids, the configuration is always in cis configuration, meaning the hydrogens are located side by side. Okay, so that could be the cis configuration of that double bond, or another one, a cis configuration of that double bond. So this cis double bond can result in a bent chain, which does not allow fatty acids to pack as close together and consequently lower the melting point. So remember, when we have unsaturated fatty acids, it will form, the double bond will form a kink in the structure. So this kink results to the fatty acids not to pack as close together. So in consequence, those unsaturated fatty acids has lower melting point compared to saturated fatty acids. So they can melt easily. And free form of fatty acids are rarely found in nature. So normally they are part of the complex lipid molecules. So take note that when we have fatty acids, they have even number of carbon atoms. We can have the long chain fatty acids, which is carbon atoms that range from 12 to 26. We have medium chain of fatty acids, which has carbon atoms that can range from 8 to 18. We can have short chain of fatty acids that can have carbon atoms that can range from 4 and 6. Okay? So the fatty acids present in naturally occurring lipids almost always have the following characteristic. They have unbranched carbon chain, an even number of carbon atoms in the carbon chain, and they also have double bonds when present in carbon chain in cis configuration. So you have to remember that. So under saturated fatty acids, meaning we only have that straight chain of fatty acid. And we can have its carboxyl group right here. But for unsaturated fatty acids, meaning already having one or more double bond in the structure. So example, this is the fatty acid that is even in number 1, 2, 3, 4, 5, 6, 7. So like 8. 1, 2, 3, 4, 5, 6, 7. Example, 1, 1, 2, 3, 4. So let's have 4. Then 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8. So this can have a kink in the structure because it has one double bond in that structure. So once you have one double bond in the structure, meaning we have mono unsaturated fatty acids. But when we have multiple of double bonds in that fatty acid structure, we can call it as PUFAs or polyunsaturated fatty acids. Okay, so we can see here that we have a double bond, and the configuration of the hydrogens right there is in cis configuration, and this double bond gives a kink in the structure that results for the carbon to carbon bonds in this fatty acid to not pack closely, and this will result to lower melting points of this unsaturated fatty acid. So this is a image of saturated fatty acid. So this is a fatty acid with a carbon chain in which all carbon to carbon bonds are single bonds. So this is an example of the structural formula of a 16 carbon saturated fatty acid. Example here is we have this palmitic acid, or we have this hexadecanoic acid, or this could be the condensed form of this palmitic acid, and this is the line angle structural formula of this palmitic acid. So once you see COOH, that means that we are having carboxyl group in the structure, carboxylic group in the structure. And let's talk about monounsaturated fatty acids. So these are fatty acid with a double bond in the structure. However, it can only contain one double bond. Take note that you can see here the double bond that creates a kink or bend in the structure that literally affects the physical properties of the this fatty acid. So due to the kink, the carbon to carbon cannot pack well. Therefore, those fatty acids with double bonds have lower melting point. And when we say polyunsaturated fatty acid, meaning we can have two or more double bonds in the fatty acid structure. So you can have up to 6 double bonds are found in biochemically important polyunsaturated fatty acids, and examples of this important PUFAs include this linolenic acid, which is an omega-3 fatty acid, and this linoleic acid, which is an omega-6 fatty acid. So these are examples of PUFAs. So these are the additional physical properties of fatty acids. So they are largely determined based on the length of their hydrocarbon chain and degree of unsaturation of the hydrocarbon chain. So as the chain length increases, you have to remember that its melting point also increases. So at increasing chain length, you have also an increasing melting point. So you can see here increasing chain length. As you increase the chain length, your melting point also increases. And also, as you increase the chain length, you also increase its solubility. Okay? I know you actually decrease your solubility. So, your long chain lipids are less likely to dissolve in water because it has a big group of hydrophobic hydrocarbon in that structure. Again, as you increase the chain length, you lower or you decrease the solubility of that fatty acid in water. So this is not HO2, but this is just H2O. And we will be talking about the water solubility properties of fatty acids. So take note that the nonpolar hydrocarbon chain accounts for the poor solubility of fatty acids in water. And take note that the solubility decreases as the carbon chain length increases. And the slight solubility of short fatty acids is related to the polarity of the carboxyl group present. So they can have slight solubility due to that carboxyl group. However, as a whole, your fatty acid is not really soluble because of this great surface area of your hydrocarbon chain in that structure. So take note that in longer fatty acids, the nonpolar nature of the hydrocarbon chain completely dominates the solubility consideration. So if you are going to be tasked to compare the solubility of your fatty acids in water, you have to count the number of carbon present, because at increasing number of hydrocarbon, meaning its solubility in water also decreases. So let's talk about the melting points of fatty acids. So take note that melting points increase with increasing molar mass. So we will have a hard time to dissolve a specific compound once its molar mass also increases. Or once we have higher number of hydrocarbon chain, meaning we have greater extent of that London dispersion forces in that structure. So the longer the carbon chain, we have higher melting point of that fatty acids. So we can see here that an example is that we have this saturated fatty acids here with 12 carbons, and we also have this saturated fatty acids with 20 carbons. So you can see here that as the number of carbon atoms increases, we also have an increase in temperature that we require in order to melt those fatty acids. So in this case, when we have 12 carbons, we can melt this kind of fatty acids at about 45 degrees Celsius. But when we have 20 carbons in that hydrocarbon chain of fatty acid, we can use 70 degrees Celsius of heat in order to melt them. So at increasing number of carbons, the melting point also increases. So take note that the presence of double bonds lowers the melting point because there is no tight packing in the structure. So when you have double bond, it creates a kink. So the molecules have lesser attraction to each other or lesser attraction to the chain. So it has lower melting point. So these are additional properties of fatty acids. Take note that lipids contain many different fatty acids, and fatty acid chain length and degree of unsaturation affect the melting points of lipids and fluidity of lipids. So meaning if there are a lot of number of double bonds, meaning we have more fluid na fatty acid. But when we only have lower number of double bonds, or we can only have single bonds in that fatty acid chain, meaning we have more rigid. So we have rigid, lower number of double bonds. I will just name it as DB, meaning we have more rigid structure. The rigidity of the structure increases. So for saturated fatty acids, you have to remember that they are packed close together. So they are less fluid, so they have high rigidity. And since they are closely packed together, they have higher melting temperatures because it takes more energy to break the interactions. So these saturated fatty acids are actually or likely to be solid at room temperature, while these unsaturated fatty acids do not pack as closely. So they are more fluid than saturated fatty acids, and they are considered to have lower melting points than saturated ones, and they are likely to be liquid at room temperature. So take note that when we have double bonds in our fatty acid, we have the cis configuration of that double bond. So once the configuration is cis, we can have the cis fatty acid. So the cis fatty acid has its hydrogen on the same side of the double bond, and cis molecules fold back into U-like formation. So mura siyang nag-U diha. Most naturally occurring unsaturated fatty acids are cis, while there are also trans fatty acids. So once you say trans fatty acids, they have hydrogens on the opposite side. You can see here that this hydrogen is on this side and this hydrogen is on this side. So trans molecules are more linear, so they don't have the U-like formation in the structure. So the trans form typically occurs in partially hydrogenated foods when hydrogen atoms shift around some double bonds and change the configuration from cis to trans. So normally, those in industries, from cis fatty acid, they are actually converting that into solid ones for easier packaging, and they do this via hydrogenation process. And during hydrogenation process, we cannot ensure that the structure of that cis fatty acid is what you call this is retained, so that in that case there are really trans fatty acids in the structure because of the want of the industries to convert that liquid portions of that that products into solid ones. So in that case, we have trans fatty acids due to hydrogenation. Later on, we will be talking about the controversies of those trans fatty acids in our food products. So this trans double bond allows a given fatty acid to adapt an extended conformation, and the trans fatty acids can pack more regularly and show higher melting points than cis forms. So take note that trans fatty acids are produced during hydrogenation of fish or vegetable oils. So fish oils and vegetable oils are really liquid at room temperature, but since industry wants it to be in solid form for easier packaging, then they do the hydrogenation of that products. So because diets high in trans fatty acids correlate with increase in LDL or low density lipoprotein, which corresponds to our bad cholesterol, and decreased HDL, which corresponds to our good cholesterol, it is generally recommended to avoid large amount of these fatty acids. So that's why in your daily products, you have to check the amount of trans fatty acids, because these trans fatty acids can contribute to an increase in low density lipoprotein. So in that case, we increase our risk of atherosclerosis. So those are when you say atherosclerosis, those can be a condition of the heart that inhibits it to perform its duty properly because of that build-up of fats in the tubings of our heart. So we have to be very careful not to eat of this or to minimize our consumption of these French fries, donuts, and cookies, which are high in trans fat. So in order to be healthy, we want to eat more healthy foods like fish and the vegetable oils and other products which are less processed, because when we have products that are less processed, meaning we can assure that we have less amounts of those trans fatty acids in our consumed products. So let's proceed to the nomenclature of fatty acids, or naming of fatty acids. So there is a system that exists for describing unsaturated fatty acids in terms of the number of carbon atoms in the acid and in terms of the double bond positions. So according to the IPAC nomenclature, or the International Union of Pure and Applied Chemistry, the carboxyl carbon is assigned to be carbon 1, and the carbon next to it is considered as carbon number 2, then so on until the carbon, now the last carbon atom is reached or numbered. Now, the next carbon to our carbonyl carbon is considered as the alpha carbon, while the third carbon from the carbonyl carbon is considered as the beta carbon, and the last carbon is considered as the omega carbon or the terminal carbon. So, a simplified nomenclature specifies the chain length, the number of double bonds separated by a colon. So, take note that you have to count the number of carbons in that fatty acid starting from the carbon of the carboxyl group of that fatty acid. So, example, in this structure, we have 18 carbons. Then we write 18. Then we place colon because the next item here will be the number of the double bonds. So, in this case, we have 3 double bonds. Therefore, we place colon, then number 3. And in order for us to know the position of the double bonds, we place delta, and superscript to that delta, we have carbons 9, carbons 12, carbons 15 as the position of the double bond. So in simpler form, if we have to describe this fatty acid, this should be written as they have 18 carbons with 3 double bonds, and delta represent at carbon 9, 12, and 15. So this should be the description of that fatty acid. So it has 18 carbons with 3 double bonds located at carbon 9, carbon 12, and carbon 15. So the most commonly occurring fatty acids have even number of carbons in an unbranched chain of 12 to 24 carbons. So fatty acids are named after corresponding hydrocarbons with the same number and arrangement of carbon atoms. So oic have been substituted for E. So example, we have octadecane. So meaning, last time we have 18 carbons, right? In our example, so we have octadecane. So this E is substituted with oic. So we have this octadecanoic acid. So saturated acids end in anoic acid. So we don't have a saturated fatty acid example previously. We have a unsaturated fatty acid example. So this unsaturated fatty acids ends in enoic. So you can know where are the saturated ones because they are assigned as anoic acid, octadecanoic acid. But when we have unsaturated fatty acid, like we have in our previous example, we can call them as octadecanoic acid if it has 1 double bond. If it has 2 double bond, octadecadienoic acid, di, due to the 2 double bonds. And in our case previously, we have that octadecatrienoic acid because it has 3 double bonds. And of course, it is unsaturated. So that is how you name your fatty acids. So in this example, we have this saturated fatty acid which has 16 carbons. You have 0 right here because you don't have a number of your double bond. So that is named as hexadecanoic acid. For 18 carbon fatty acid, it can have this cis-9 because it has a kink in carbon 9. When we start our numbering here from the carboxyl group of our carboxylic acid na carbon 1 siya. Then continue ta carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8, carbon 9. So the double bond is located at carbon 9. Now, it has, if we are going to continue the numbering, we have 10, 11, 12, 13, 14, 15, 16, 17, 18. Therefore, it has 18 carbons in the structure. So when we have 18 carbons, we have to write it here. Then we only have 1 double bond. one double bond, then we have to place delta and write write it in the superscript to which number of carbon in the structure can we locate this double bond. So it can be located at carbon 9. So we place 9 here as in the superscript. So the cis-9 octadecenoic acid is an oleic acid. And also, if we are going to count this chain of fatty acid, we have 3 double bonds right here located at 9, 12, and 15. And we have a total of 18 na, carbons in that fatty acid. So we have 18, 3 for 3 double bonds, then delta because those double bonds are located at carbon 9, 12, and 15. So 18, 3, delta 9, 12, and 15. And this can be named as cis 9, 12, 15, the location of your double bonds, octadecatrienoic acid, or this is the lenolic acid. So there are also exceptions to the rule. A notable exception to this generalization is that biochemically important arachidonic acid, a PUFA with the structural parameters of 20 carbons with 4 double bonds located at 5, 8, 11, 14. So we term that as arachidonic acid. We have this icosapentanoic acid with 5 double bonds and docosahexanoic acid with 6 double bonds. So they can be an exception to the rule in naming of fatty acids. You can see here that you have docosa and icosa. So those are exceptions to the rule in the nomenclature of fatty acids. Take note that your DHA is very important fatty acid, especially found in the milk of our babies because it actually functions as it has an essential function for brain development. So it can also have a important function for your eyes and can reduce the risk factors for your heart disease. So DHA is actually a fatty acid which is named as a docosahexanoic acid. So you can see here that we end our name of this fatty acid into anoic. Remember, they are polyunsaturated, and normally when you have polyunsaturated, we end them with enoic. But your EPA or icosapentanoic acid and docosahexanoic acid are exception to the rule. And next, we have to talk about this additional nomenclature of fatty acid in unsaturated fatty acids. So take note that we call the last or terminal carbon as the omega carbon. And the double bonds counting from the methyl ends are the omega desaturation. So if last time we are focusing to number the carbon chain from carbon number 1 here in the carboxyl group, now we have to look at the omega end. So once it is near to the omega end of the double bond is near to the omega end of our structure, we call those double bonds as omega desaturations. And this is a common nomenclature. The carbon farthest from the carboxyl is called the omega carbon. And why do we have that omega-3 fatty acids? Because counting from this omega carbon, it has a double bond in that third carbon, counting from that omega carbon. So 1, 2, 3, meaning it has a double bond to that carbon. So that's why we have that omega-3 fatty acid. And we also have omega-6 fatty acids. So we count first from that omega carbon or that terminal carbon. And then as we continue to count, we can locate that the double bond is located at the carbon 6, starting from that omega carbon. So we term those fatty acids as omega-6 fatty acids. So linolenic acid is an omega-3 fatty acid, and linoleic acid is an omega-6 fatty acid. So it starts to count at the metal end or at the omega carbon, and at linoleic acid you can find the saturation at the third carbon from the omega, and the saturation of this what do you call this, unsaturation of this linoleic acid at the carbon 6 from this omega end of our unsaturated fatty acid. So that's why we have omega-3 and omega-6 fatty acid. So these are the summary of your saturated fatty acids and their common name: monounsaturated fatty acids and polyunsaturated fatty acids. So magbalik-balik rani. So you have to be familiar with all of this. So you can check your learning about this with these slides, and it also have answers. You can do this on your own. And let's talk about cis and trans fatty acids. So when triacylglycerols in vegetable oils are subjected to partial hydrogenation, two types of changes occurs in the fatty acid residues present. Some of the double bonds present are converted to single bonds, and some of the cis double bonds are converted to trans double bonds. So this is the effect of hydrogenation. And take note, we have to be very careful in consuming these trans fatty acids products, or products which has a high amount of trans fatty acids, because it can raise the number of the bad cholesterol, and it can raise the number of bad cholesterol, thereby giving a lot of disease in the body. Now, we also have essential fatty acids. So, fatty acids doesn't only contribute to bad ones, but mainly they have really big roles in our body. And essential fatty acid is a fatty acid needed in the human body that must be obtained from dietary sources because it cannot be synthesized within the body. So, we have to supply those essential fatty acids rather than those trans fatty acids. So the two important fatty acids that can be consumed are this linoleic acid and linolenic acid. So we can find these fatty acids in plants and fish oil. So as you can remember, your tuna has an advertisement that they have omega-6 fatty acids, which are good for the heart. So those are good for consumption for humans because they have good effects in our body, and they are essentially important fatty acids to be supplied in humans. Okay, so you have to choose those products that have essential fatty acids rather than trans fatty acids. So these are omega fatty acids, the linoleic acid and linolenic acid. They are needed for proper membrane structure, and they also serve as starting materials for the production of several nutritionally important longer chain of omega-6 and omega-3 acids. And when these two acids are missing from the diet, the skin reddens and becomes irritated. So there are infections and dehydration, and the liver may develop abnormalities. So we really have to supply our body with enough of omega fatty acids. If the fatty acids are restored, then the condition can reverse. So these bad conditions can reverse when we can supply our body with enough omega fatty acids. And infants are especially in need of these acids for their growth, and human breast milk has much higher percentage of the essential fatty acids than cow's milk. So those are the different benefits of omega fatty acids in our body. So again, we have to supply our body with these essential fatty acids rather than those trans fatty acids found in processed foods. So let's talk about linoleic and linolenic acid. Linoleic acid is starting material for the biosynthesis of arachidonic acid. When you can hear arachidonic acid, meaning that fatty acid has 20 carbons. So again, it is a starting material. Linolenic acid, it has 18 carbons, which can be transformed to arachidonic acid, which has a 20 carbon. So take note that this arachidonic acid is involved in many biological processes in our body. So when you do not supply proper amounts of linoleic acid in the body, meaning it cannot continue to synthesize arachidonic acid, which are important substrates in different enzymatic processes in our body. So diyan na din mag-start og problema ang imong body. It can form a lot of diseases or abnormalities due to insufficient amount of that essential fatty acid supplied in the body. So take note, this arachidonic acid is the major starting material for eicosanoids that help regulate blood pressure, clotting, and several important body functions. On the other hand, linolenic acid is said to be the starting material for the biosynthesis of two additional omega-3 fatty acids, which is the EPA and the DHA. So take note that DHA is important for brain development and function. So if you doesn't supply enough amount of linolenic acid, therefore that could lead to low communication of your brain and different diseases in which your EPA or eicosapentaenoic acid and DHA are connected. So you really have to supply this linolenic acid in your body. So they are important constituents of communication membranes of the brain and are necessary for normal brain development. So without linolenic acid, we cannot have this EPA and DHA. So we really have to make an option, or we really have to consume greatly the amount of this linoleic and linolenic acid because they are essential for our body. So these are the, these are the summary of the fatty acids. You can have saturated, monounsaturated, polyunsaturated, and under our monounsaturated, we can have the configuration based on cis and trans. Remember that cis unsaturation are more healthier than trans unsaturation, and under the polyunsaturated fatty acids or PUFAs, we can have our omega-3 and omega-6. So again, this can be the different classification of our lipids. So we already talked about fatty acids. So after fatty acids, we will be talking about triacylglycerols or TAGs. So in the structure of triacylglycerols, you have 3 fatty acids combined with this glycerol. So you have a dehydration process here in order to connect this glycerol with this fatty acid. Triacylglycerol because you have 3 fatty acids connected to this glycerol, or you are forming a triester of glycerol. Okay, so these are glycerol containing lipids that are produced from the esterification of glycerol with one or more fatty acids. So we are forming here an ester linkage between this glycerol and fatty acid. So once you say glycerol, meaning it is a 3-carbon hydrocarbon with 3 hydroxyl group on that each of the carbon. So triacylglycerol or triglycerides is a lipid formed by the esterification of 3 fatty acids to glycerol molecule, and this actually serves as energy storage in adipose cells. So once you say adipose cells, those are the fat cells. Okay, they are energy storage in adipose cells. So this is the general structure of your TAGs or triacylglycerol. In order to connect the fatty acid and glycerol, you have your ester linkage and ester linkage. So once you have one fatty acid connected to that glycerol, you have monoacylglycerol. Once you have 2 fatty acid connected to that glycerol, you have the 1,2-diacylglycerol. Once you have an additional fatty acid connected to that 1,2-diacylglycerol, you can form your triacylglycerol. So each OH in the glycerol can react with a fatty acid. You start with carbon 1, next carbon 2, and carbon 3. So in order to form the ester linkage, there is always a release of water or a dehydration process going on. So let's go to the nomenclature of triacylglycerol. So those contain the same kind of fatty acid in all three positions are called as simple triacylglycerol. So you only have one fatty acid group. So that could be a simple triacylglycerol. So they can just be named after the fatty acid that they contain. So example, you have used palmitic acid, then we can name it as tripalmitin. If it has stearic acid, therefore it is tristerine. If it has oleic acid, therefore it is triolane. So if we have mixed triglyceride, meaning we have different fatty acids connected to it. So most fats and oils are mixed triacylglycerol. So in this case, you can name it depending on the fatty acid connection. So you have to label where is the carbon 1 in your glycerol, carbon 2, and carbon 3. Then you can name that as, example for this, you have stearic acid in carbon 1, you have linoleic acid in carbon 2, and you have this palmitic acid in carbon 3. So you have this 1 steroyl, 2 linoleal, and 3 palmitoyl glycerol. So that is how you name your mixed triglyceride. So most naturally occurring tags are mixed, really mixed in nature. So those simple tags rarely exist. And take note to name this compound unambiguously. The name and position of each fatty acid must be specified. So when unsaturated fatty acids are present, they are located at carbon 2. So you can see here that this linoleic acid is located at carbon 2. So you have to label where is your carbon 1, carbon 2, and carbon 3. And then from carbon 1, you start naming. If you have stearic acid, then that is steroyl. Then at carbon 2, you have your linoleic acid, then you have your linoloyl. Then at carbon 3, you have your palmitic acid, so you have your palmitoyl. So this is the name of this triacylglycerol. So you can have this activity, and the answer is already in this slide in order to check your learning. So let's go and discuss the properties of your tags or triacylglycerols. So triacylglycerols in natural fats and oils are nonpolar. They are hydrophobic molecules with no ionic charges, and they are insoluble in water. So they have lower specific gravities or densities than water, which explains why mixtures of oil and water have two phases. The oil floats on the aqueous phase. So that are the properties of your triacylglycerol. So let's go now to fats. So when you say fats, these are just mixture of triacylglycerols. That is solid because it contains a high proportion of your saturated fatty acids. So these are composed mainly of straight chain fatty acids, and they are composed mainly of saturated or trans fatty acids. So they are packed closely together, they have higher attractive forces, and higher melting points. So in animal fats, they are composed mainly of saturated fatty acids rather than unsaturated ones. So we can have an example of a beef tallow, the major component of beef tallow, which is a tristerine. This is the saturated triglyceride. So we can have this as solid in room temperature because of the tight packing of your saturated fatty acids. And you also have oils. Oil is a mixture of triacylglycerol that is liquid because it contains higher amount of unsaturated acid. So it can have it can be a mono or polyunsaturated fatty acid. So it cannot pack closely because it has a double bond in the structure, or cis double bond in the structure that causes kink. So since they are not tightly packed, their intermolecular forces are weaker and they have less energy to separate the molecules, and they can actually have lower melting point. So we have examples here like corn oil and olive oil, which are liquid at room temperature because they are made up mostly of these unsaturated fatty acids. So fats versus oil. If you are going to compare them, your animal fats has high amount of saturated fatty acids, while your vegetable oils has higher amount of unsaturated fatty acids. Take note that your vegetable oils are much more healthier compared to your animal fats. So you always have to choose the higher amount of unsaturated fatty acids in our food products rather than the higher amount of saturated fatty acids. So you can check here the different amount of your saturated fatty acids and unsaturated fatty acids, and you have the option to choose which is more healthier. Now, lipids are considered as structural elements, and if you're going to look at them closely, they have different, what you call this, they have different parts in that cell membrane. You can see there is a glycolipid, there is a phospholipid, there is a peripheral protein, there is an integral protein, there is a lipid bilayer, and there are oligosaccharides of glycoprotein. So it actually is a simple structure, but looking at it closely, there are different complexities in the structure. So once you say cell membrane, this is a lipid-based structure that separates the cell aqueous base interior from the aqueous environment surrounding the cell. And normally this is its structure. It has an interior polar heads, and the central structure is the central non-polar tails. And it also have this exterior polar heads. So this is an example of your cell membrane. So in the outer portion, we can find the hydrophilic surfaces, while in the inner portion, we can find the hydrophobic tails. So the cell membrane controls the movement of substances into and out of the cell. So take note that up to 80% of the mass of a cell membrane is lipid material consisting primarily of three types. We can have this phospholipids, glycolipids, and cholesterol. So once we say phospholipids, those are complex lipids which has phosphate in this group in their groups. Once we have glycolipids, those are still lipids with sugars attachments, okay, or sugar attachments. And once we have cholesterol, cholesterol is under lipids. However, they are, what do you call this? They're in solid structure compared to our fatty acids and triacyl glycerol. So you can see later that we have a ring structure for cholesterol. So you have to remember that we have phospholipids, glycolipids, and cholesterols that can be found in our cell membrane. So once we talk about phospholipids, they are actually abundant in all biological membrane. Their bipolar nature is central to the structure and function of the membrane. Now, the primary structure of your phospholipid is that they act as emulsifying agent at cell membrane surfaces since it contains both polar and nonpolar component. If you are going to if you are going to check the structure of your phospholipid, they can actually be divided into glycerophospholipid and sphingolipids. So in this glycerophospholipid, you have to take note that there is a glycerol here connected to fatty acid, and a phosphate group connected to an alcohol. So that is a glycerophospholipid. But once we have sphingolipids, we have this sphingosine na main group niya, connected to one fatty acid, connected to a phosphate group, and a choline. So those are the phospholipids. So you can do this activity on your own, and the answer is actually here. Now, let's talk about glycerophospholipid. So, lecithin is an example of your glycerophospholipid. So, it has a glycerol in the structure, then it has a fatty acid. It has a phosphate group, and it has a choline. So, this is the general structure of your choline, a quaternary ammonium ion. So, once you can see this kind of structure, meaning you have your glycerophospholipids. So, examples of these glycerophospholipids involve ethanolamine and also your phosphatidylethanolamines and phosphatidylserines, which are also known as cephalins. Okay? So, your cephalins has an important function in cell membrane and brain tissue. So, those are your glycerophospholipids. Now, let's go to your phosphoglycerides. Phosphatidylcholine or lecithin and phosphatidylethanolamine are two common phospholipids found in membranes. Their primary function is to act as emulsifying agent at the cell membrane surfaces since it contains both polar and non-polar component. So your phosphatidylserine and phosphatidylethanolamine play an important role in the process of blood clotting. So nga na lang ilang structure, but they have very important roles in our body. Now, let's go to sphingolipids. So, once you have sphingo, meaning you have this sphingosine nga iyahang head or iyahang main chain. So, this is the formula for your sphingosine or the structure in which a fatty acid can be connected and a phosphate group can be added. Okay? So, the simplest compounds under sphingolipids are ceramides, which consist of one fatty acids linked to the amino group of the sphingosine by an amide bond, and ceramides natural lipids and are a major component in the skin structure. So take note that ceramides are natural lipids that are major component in the surface of skin structure. So this is a sphingosine, and this is an example of your ceramide or your N-acyl sphingosine. And let's go to the sphingophospholipid. So, last time, the sphingosine lang to. I'm sorry if I misinterpret it nga na ay phosphate group ka ganyan. Wala yung phosphate group ang imong sphingosine. Let's go to the sphingophospholipid. Sphingophospholipid is a lipid that contains one fatty acid and one phosphate group attached to the sphingosine molecule and an alcohol group attached to the phosphate group. So, na siya sphingosine structure, via amide linkage, naka-attach imong fatty acid, via ester linkage, naka-attach imong phosphate group, and via ester linkage, naka-attach ang imuhang alcohol. So, you have here your sphingophospholipid general structure. And this is the chemical structure of your sphingosine. So, sphingomyelins are under the sphingophospholipid. So, in which the alcohol esterified to the phosphate group is choline are called these sphingomyelins. So, in this case, you have your sphingosine, sayang amino group, naka-attach yung steric acid, then a diphosphate, then connected to choline. Sphingomyelins are found in all cell membranes and are important structural components of the myelin sheath, which are protective and insulating coating that surrounds the nerves. So, another example for this, we have these sphingoglycolipids na. Humanata sa sphingophospholipid, din ta sa sphingoglycolipids. Take note, kung natay glyco, naagyoy sugar. So, it's just a sphingosine, fatty acid via amide linkage attached to your sphingosine, and via glycosidic linkage, your monosaccharide or oligosaccharide is connected. So, a sphingoglycolipid is a lipid that contains both fatty acid and a carbohydrate component attached to the sphingosine molecule. So, the simplest sphingoglycolipids are the cerebrosides, which contains a monosaccharide unit, which are either glucose and galactose. And there are more complex sphingoglycolipids, which are the gangliosides, which contain branched chain up to 7 monosaccharide residues, and these substances occur in gray matter of the brain as well as in the myelin sheath. So the gangliosides are actually the determinants of our blood group. From our carbohydrate topics, we talk about the uh, glycans attached to these different blood groups. However, if you are going to look at it closely, we are actually having gangliosides in our blood group. So there are sphingosine, fatty acids, then attached na din na ato ang glycans. Okay? So, um, these are the different categories of the classification of lipids based on their use in the body. So, you have energy storage lipids, which are your glycerol. You have your membrane lipids, in which you have your glycerophospholipid, sphingophospholipid, and sphingoglycolipid. And we have a combination of these phospholipids and glycerol. We can have this glycerolipids, and a combination of phospholipids and sphingoglycolipid. We can have our sphingolipids. So these are actually general structures of your membrane lipids or connection niya sa each other. So you just have to look at the legend. Then, let's go to the membrane lipids, which are the cholesterol. So, cholesterol molecules are components of cell membrane. So, it doesn't mean nga cholesterol siya, dili na siya essential sa atong body. Because if you don't have cholesterol, meaning, ang ato biyang cells are composed of, cell membrane. So, dili maka-function properly atong cell membrane without proper amounts of cholesterol. So, we need to have proper intake of cholesterol but in proper amounts lang. So, this cholesterol actually regulate the membrane fluidity and rigidity. Because of their compact shape, cholesterol molecules fit between the fatty acid side chain of the lipid bilayer, restricting the movement of fatty acid side chain and making the bilayer more rigid. So, kung naay cholesterol, meaning mo insert siya diha dapita. And then it makes the structure more rigid. Mas gahi, dili kayo siya fluid. So, take note that your cholesterol has this structure. It is actually a 27 carbon steroid molecule that is component of the cell membranes and precursor of other steroid-based lipids, including bile acids, steroid hormones, and vitamin D. So once you know the cholesterol, naagi ni siya steroid nga tawag ani main group. Okay? Mo ni na siya 3 kabuok ka 6-membered ring and a 1 5-membered ring. So this is the structure of your steroids and naapod ang iyang numbering diha. So imong cholesterol has a steroid in its structure. So mo nang gaparigid sa cell membrane because the structure itself sa imong cholesterol is already rigid. Now, we also have emulsification lipids nga makita sa itong bile acids. So, once you say emulsifier, these are substances that can disperse and stabilize water-insoluble substances as colloidal particles in aqueous solution. So, bile acid is a cholesterol derivative that functions as a lipid emulsifying agent that facilitate the absorption of dietary lipids in the intestine. Kaya kung wala kay emulsifier, meaning dili kay ma-dissolve tong substances which are hardly soluble in your water. Therefore, dili ma-absorb sa imong intestine ang proper nutrition. So, you need those bile acids. And these bile acids are derivatives of cholesterol. So, once you say derivatives of cholesterol, meaning naalay gamay sa structure nga gi-change. So, this is cholesterol. So, kanin natin cholic acid. From this group, na-change lang diri. We have this deoxycholic acid na kanipod ang na-change. And deoxycholic acid nga additional sa cholesterol is kani, and kani. So, that is why we term them as derivatives of cholesterol. So they are very much important as important emulsifying agent. Also, we have steroid hormones, which are considered as our messenger lipids. Steroid hormones and eicosanoids are two large families of lipids that have messenger functions. A hormone is a biochemical substance produced by ductless gland that has messenger functions, serving as means of communication between various tissues. Some hormones, though not at all, are lipids. So your steroid hormones is a hormone that is a cholesterol derivative. So you can have two classes of steroid hormones. You can have your sex hormones, which control the reproduction and secondary sex characteristics, and this adrenocorticoid hormones, which regulate the numerous biochemical processes in the body. So we can have these sex hormones. You have estrogens, androgens, and progestins. So estrogens are female sex hormones, which are synthesized by the ovaries and adrenal cortex and are responsible for the development of female secondary sex characteristics at the onset of the puberty for the regulation of the menstrual cycle. And your androgens are male sex hormones. They are synthesized by the testes and adrenal cortex and promote the development of the male secondary characteristics, while your progestins are pregnancy hormones. They are synthesized in the ovaries and the placenta and prepare the lining of the uterus for the implantation of the fertilized ovum. So they also suppress the ovulation. Now, these are the structures of your estrogen, testosterone, and you can see, you can look at them. Naagid ang steroid nga structure. So, maunang they are the steroid called as steroid hormones. So, additionally, you have your adrenocorticoid hormones or your glucocorticoids that they control the glucose metabolism and counteract inflammation. So, the major glucocorticoid is cortisol. Then, cortisol is a hormone that is synthesized or made up in large amount by the adrenal glands and is synthetic ketone derivative. Cortisol exert powerful anti-inflammatory effects in the body. So, muna tong body, they have the capability to heal on their own because we have hormones responsible for that. Kung dili na makaya sa atong mga kanang anti-inflammatory hormones, muna nang mo-supply na ta dapat og mga tambal sa atoang body. And also, there are mineral corticoids which control the balance of sodium and potassium ions in cells and body fluids. And the major mineralocorticoid is called the aldosterone. So we also have these messenger lipids, which are eicosanoids. So when you say eicosanoids, meaning naagid sila 20 ka-carbon sa ilahang structure. So they are actually arachidonic acid. So almost all cells except red blood cells produce eicosanoids. So eicosanoids exert their effects in tissues where they are synthesized. So the physiological effects of eicosanoids include the mediation of inflammatory response, production of pain and fever, regulation of blood pressure, induction of blood clotting, production of control of reproductive functions, and regulation of sleep or wake cycle. So take note ha, inyong eicosanoids or your arachidonic acid cannot be synthesized once wala ka nag-supply sa tong body og essential fatty acids. So we need to supply our body with essential fatty acids para makasynthesize siya og eicosanoids and para makabuhat siya sa following niya nga physiological function. So we have messenger lipids nga eicosanoids. We have the prostaglandins, which is a 20 carbon fatty acids derivative that contains a cyclopentane ring and oxygen functional group. We also have leukotrienes. This is a derivative of the arachidonic acid, and a thromboxane nga derivative gihapon sa kaning atoang arachidonic acid. So this thromboxanes is to promote the formation of blood clots or kanang involved siya sa blood aggregation. So Ang kaning ato ang prostaglandins and leukotrienes are actually related to the inflammation process. So again, kung wala tay proper nga supply sa tong arachidonic acid, meaning our enzymes doesn't have enough substrate in order for them to act and perform their duties. So we also have these protective coating lipids, which are biological waxes. Waxes are complex mixtures of esters of long chain of carboxylic acids and long chain alcohols, and a wax is a mixture of carboxylic or fatty acid and long chain alcohol which forms monoesters. So the acids usually have an even number from 16 to 36 carbons, and the alcohol have an even number from 24 to 36 carbons. So the plant leaves have a biological wax coating to prevent excessive loss of water. So mo nang shiny atong plants because it has biological waxes. So it has long chain of fatty acid connected to the ester linkage of that long chain of alcohol. So these are different example of wax. You can read it on your own. Yun. We also have this earwax, or what we call the cerumen. This is not actually a wax, but these are primary components of earwax are shed layers of skin. 60% of earwax consist of keratin, and 12 to 20% of saturated and unsaturated long chain of fatty acids, alcohol, and squalene, and nag-contain po siya 6 to 9% of cholesterol. So these are the schematic diagram of the different functions of your lipids, including their groups. Okay, you just have to read that. So again, you have your saponifiable lipids and non-saponifiable lipids. You already discussed that. And these are a summary of your types of linkages in 5 kinds of saponifiable lipids. And classification based on their complexity. And also, you have your derived lipids, which are the vitamins nga insoluble in water. So, may kag vitamin, vital amine. So, this is a vital compound in the body. So, the term vitamin applies to any compound or closely related group of compounds satisfying the following criteria. An organic rather than inorganic element. It cannot be synthesized at all. That's why we need to supply them. Its absence causes a specific vitamin deficiency disease, and its presence is essential to normal growth and health. And also, it is present in food in small concentration, and it is not a carbohydrate and a saponifiable lipid, amino acid, or protein. And it actually functions in the body either as a precursor for coenzymes or as coenzymes themselves. So we have isoprene vitamins. Once you say isoprene, meaning it has a 5 carbon unit. So 5, 5, 5. So we can have this isoprene vitamins, which is vitamin K, which has an important role in blood clotting. Okay. So our lipid-soluble vitamins are this. So you just have to remember vitamins ADEK, vitamin A, D, E, and K. So vitamin A serves as the site for primary photochemical reaction in vision. Then vitamin D regulates the calcium metabolism. Without proper amounts of vitamin D, your intestines cannot absorb the necessary amount of your calcium in order for your bones to be stronger. Then vitamin E serves as antioxidants. So, and vitamin K has regulatory function in blood clotting. So you just have to remember that you have your lipid-soluble vitamins, ADEK, A, D, E, and K. Now, this is the structure of your vitamin A. This is the molecular formula. And the main sources are the cod liver oil, fish liver oils, animal liver, and dairy products. And provitamin A is found in carotenes. Then provitamins have no vitamin activity. However, upon ingestion, then mag-undergo siya metabolism. There is a specific chemical reaction that will cleave the central carbon-to-carbon double bond to give the 2 molecules of vitamin A. When you say cleave, meaning mabroke. So, this is the site of your cleavage sa vitamin A via enzyme catalyzed cleavage, then maka-synthesize din siya of vitamin A. 2 vitamin A, duha ka buok ana. Okay, cleave lang na niya. Now, vitamin D is good for the regulation of calcium and phosphorus. You have your vitamin D2 or your ergocalciferol and vitamin D3 or cholecalciferol, in which your fish liver oils are the richest source. So these are the different structures of your D2 and D3. And your vitamin D, the pigment in the skin, the 7-dehydrocholesterol is a provitamin D. And when it is irradiated by the sunlight, it converts into vitamin D3. So munang kanatong ginapang intake ng vitamin D, dili pa gina siya effective once wala nato siya gi-expose sa sunlight. So naman ang kinahanglan ta magpainit kay dili gihapon nato na makuha atong proper nga vitamin D kung wala ta nagpa-expose sa sunlight. Dili nato ma-achieve ang atuang cholecalciferol. So naman ang mga bata, para dili sila magka-rickets, ginasupply sa mothers ang ilahang milk as well as ang vitamins and ginapa-initan kay para ang provitamin D3 ma-convert to vitamin D3, which is the cholecalciferol, then further na puday na siya ma-convert into the ergocalciferol and do its duty dito sa body. Kay kung dili nimo painitan ng isa ka bata, rickets can be a problem or kana siyang dili kay healthy ang bone and then mura siyang bakang ang bata kay tungod lagi walay proper absorption of calcium sa iyahang bones. Kay kung wala kay vitamin D, meaning dili kay maka-absorb ang imuhang calcium sa imuhang intestines. So this is an example of a kid without the vitamin D treatment, then after 14 months of vitamin D treatment. Munang importante atong vitamins because our body cannot supply all we need. We need to eat proper foods kay para mahimo tang healthy. And vitamin E is the alpha tocopherol. So these are the main components sa inyong mga Myra E. Ngano makapablooming si Myra E? Because those are antioxidants. Gina-prevent niya ang damaging effects sa imuhang free radicals. So dili kay mamatay ang imuhang cells, or it has the capability to fight mga mga bad objects sa imuhang body. So munang mas mag-blooming ka. And vitamin K is important for blood coagulation. Again, it has isoprene units or 5-carbon units sa ato ang vitamin K. And we have biological function of lipids. Take note that lipids are known as fats that provide major way of storing energy and carbon atoms in the body. So normally, ang ato ang lipids actually, it has a higher taas siya og mahatag sa ato ang energy compared sa katong energy nga gina-provide sa carbohydrates. Mao nang kung mag-diet ta, ang atong adipose tissue, ang atong adipose kibali atong mga fats, mugamay na siya kay gaka-consume na siya sa body. Mura magud silang storage sa atong body nga in case nga wala nay makaon, katong mga fats ang hinahinayon og consume. And also without those lipids, meaning wala po tayo ka ng mga fat-soluble vitamins. We need those fat-soluble vitamins in order to function properly, which are your addict. And also, kato sila acts also as coenzymes, especially your coenzyme Q, in which your ATP synthesis in mitochondria involved in coenzyme Q. And also your vitamin K is a coenzyme that is very much helpful in blood clot formation. And another function of your lipids is that they are water repellent. So remember that they can be biological waxes in plants. So mo na siya ang kanang another function niya. And it is mainly important constituent of the nervous system. Unang mga functions of lipids. So another function sa itong lipids is that they surround and insulate vital body organs, providing protection from mechanical shock and preventing excessive loss of heat energy. So muna mga tambok kay nga people dili kay dali mamugnaw because they have proper insulation. And your phospholipids, glycolipids, cholesterol are basic components of your cell membranes, and several cholesterol derivative function as chemical messengers within the body. Dayon, signaling molecules, you have your steroid, growth factors, vitamin A, D, and you also have your light-absorbing pigments, kung wala tayong ana, meaning dili ta kakita properly, no? And we also have your intracellular messengers, nga phosphatidylinositol, antioxidants, and emulsifying agents, na makita sa tong bile salts, and also dietary fats. So, without lipids, we cannot function properly. So, dili manaway anang kanang na chabihon or whatever, we really have to achieve our proper BMI, but dili na pod sa point nga niwang nakaita nga wala na tay lipid because we cannot be considered as healthy individuals. Kung ingana na natong case.